There's still a few more people rolling in, but we'll get started at any rate. So thank you very much for joining us for today's session. We appreciate you taking the time to spend a little time with us to learn about some malware tactics. We're going to cover a technical analysis of how malware evades detections, escalates privileges, and how it persists in environments, and of course with examples and defensive strategies. My name is Cliff Jansen. I'm the CISO and VP of Security for the professional services side of things here at Arctic. Joining me on the call is Wade Guest, who is our senior security consultant and will be doing all of the demos and all the technical stuff. And of course, Robert Tran, who is our marketing person extraordinaire. So thank you very much. This session will be recorded. Once it's processed, you'll get a link with the recording. But in the meantime, if you have any questions during this, please use the chat and we'll try to answer as best we can or follow up if we need to. My newest tagline, probably been around before, but I just kind of heard it related to something completely different. But I really like it. If you aren't assessing, you're just guessing. This is really important for us on the security side. We make a lot of assumptions about different things and think that we're secure and think that our protections are in place. But if you don't take the time to do an assessment of that, you really are just guessing on that. So without further ado, I'm going to get started into talking to you first a little bit about Arctic. So Arctic is it's short for Architect Intelligence. We offer blueprints for the modern enterprise, and we cover three kind of different platforms: security, infrastructure, and platform engineering. Me and Wade, of course, are part of the security leg of that. We came about from a bunch of different companies, but we're really just Arctic now. I don't really need to explain where we came from anymore. We are just one of the fast-growing companies that are trying to get, or not trying, we're already delivering great success with all the things that we do. The way that we do this is we first take the approach of understanding your business and then making sure that we are aligned in the roadmap of whatever we need to do and can execute based on our client. We very much value our clients and want to listen to them first before we come up with any kind of ideas. And then once we have those ideas for solving whatever issues they may have, we make sure we're aligned together. And we do this using our CyberIQ methodology, which is a big wheel of different types of things. The one that we're focused on is the one at the top, the Insight IQ, where we're trying to understand what your current needs. In this case, for my team, it's on the security side, of course. We also have a managed services, which kind of encompass all these different things as well. So this is our methodology, the way we do things. And like I mentioned, our Insight IQ is one where we're currently talking about is knowing your current state and what you should focus on. So we're obviously up in the top right, the security assessments, my team, and we do a whole bunch of these types of assessments, and this is where we come across this malware that we all find. Also in our security operations centers work as well, but during the pen test. So just everybody knows this, but I'm not sure if it's still okay to have the obligatory Wikipedia page if you now have to use some sort of AI generated thing, but I just use Wikipedia. So malicious software, malware, software that's meant to design to disrupt a computer or server client, computer network, blah blah blah, in order to leak information or get access to information that they shouldn't have, or deny service. There's bunch of different types of malware, so computer viruses, worms, Trojan horses, logic bombs, ransomware, spyware, adware, rogue software, wipers, and keyloggers. But for our intents and purposes, we're just going to think about it as malicious software, and in particular, in the enterprise context, is software that's trying to get into your network, escalate privileges in your network, move around your network in order to do something that involves typically financial motivations or ideological motivations. So that's malware. So why are we covering malware as part of this as our pen test? Well, cybersecurity says, everything, all the attacks, like ransomware, at some point is going to involve malware, and most other attacks that are going to attack our enterprises are in some way going to use malware for some form, in some fashion, in order to do that. And it's changing. Malware, back when I started, malware was a little bit easier, but malware changes per instance when it's being deployed. So it's hard to catch and detect in some of the way that malware is operating, and that's what we're going to take a look at today. So enough of my chatter. I'm going to stop the chattering and turn it over to Wade in a second, right now, actually. So let's get technical.
I'm Wade. I'll be walking us through our presentation today with the demos. So we'll focus on the tactics and techniques from the MITRE ATT&CK framework that are on the slide right now. So we'll start by looking at obfuscated files or information. This isn't your typical encryption or encoding. This is kind of writing our code in a way to kind of disguise what our behavior is. We'll talk about impairing defenses. There will override some user mode protections. Will be fun to see. Process injection, which isn't going to be super interesting, but we'll walk through a straightforward way to do it. And hijack execution flow, we'll talk about DLL sideloading, which is always interesting. So we're ready for the next slide. Some of the tools we'll be talking about and seeing while we're going through this. First one is at the top there, X64DBG. I think we might see just some screenshots of this one. That tool allows us to attach to processes, set breakpoints, look at assembly instructions, look at different DLLs that have been loaded. Useful program for doing any kind of process hacking. Second one is ProcMon. So this is a Windows tool that will allow us to specify particular filters or processes and analyze any kind of registry, file, network, activity, tracks when processes or threads are created. So also very useful. And lastly, Visual Studio. This is what we'll be using to compile some of our demos. And also Visual Studio comes with this command line utility that has a program called dumpbin that we'll use in just a second here. But yeah, we're ready for the next slide. Before we get into any cool malware stuff, we're going to talk a little bit about just processes in general in the Windows operating system. So Windows provides different functions to developers to perform standard operations, think like creating a file or reading a file. That will allow a developer to essentially do those operations on the Windows operating system. We'll focus a lot today on the ones that are shown there. So requesting more memory with virtual alloc or changing permissions on memory with virtual protect. We'll talk a lot about that in a little bit. So all these functions reside in code libraries that ship with Windows by default. And when you launch a process, those code libraries are loaded into the process by default. We'll get really into the weeds there in a second. So we're ready for the next slide. So here's just an example of that. So on any Windows computer, you'll have a System32 directory, and within that will be a lot of DLL files, like shown in the screenshot there. So all those functions get put into these code libraries called dynamic link libraries, shortened for DLL, and a lot of them reside in the System32 directory. The second one from the top, NTDLL, we'll talk a lot about today. Next slide. So here's an example. So just launching notepad.exe. And so the screenshot there we see is from X64DBG. You'll see at the top, there's notepad.exe. And then there's a bunch of DLL files, most of them loaded from the System32 directory, all to help Notepad kind of do its thing. Those are all loaded by default. Next slide. And so how are some of those used? So here's just a basic example. On the far left-hand side, we have Notepad open with the text hello world, and then hit Control-S or save. And we see the save as dialog box that I'm sure we're all familiar with, where we type the name, you can hit save on a file. When we actually hit the save button, it does a couple of things, but eventually ends up going to NTDLL and calling the function ntCreateFile. And when that function runs in the bottom right there, we see the file is created, helloworld.txt, so it's actually saved on disk. But we'll really get into this workflow. So we can go to the next slide. Okay, so now we can talk a bit about malware stuff. So most of our malware today will focus on something called a loader. So the loader is responsible for loading in shellcodes, putting it into memory, changing the permissions to make sure it's executable, and then running it. This is certainly not the exclusive only type of malware. There's also kind of different workflows attackers might use to be a bit sneakier, but this is kind of our most straightforward way. So requesting space in memory, copying our bad code into that space, changing the permissions on it, and executing it. Next slide. So I use the word shellcode there. So this slide just kind of talks a little bit about what shellcode means when I mention that word today. So shellcode is assembly instructions that perform like a single task or single purpose. So basic things like executing a single command, so listing directory comments or something like that, or establishing a connection to a command and control server. So Cobalt Strike, Mythic, Sliver, Metasploit, pick your C2 framework. There will be some way to generate shellcode that when that shellcode is run, it can the process connects back to the command and control server to allow you to do all sorts of cool, complex things. So shellcode can do that, or simple things like launching a process or downloading a file. Really, all I'm trying to get across is that shellcode just means kind of single-purpose code or assembly code that performs a task. Next slide. So now we'll get into that loader workflow that we were talking about. So the line at the top there is a line of C or C++ code. And here we're calling the virtual alloc function to request space in memory to put our code. And the only thing to kind of point out in that line of code is at the very end, we're saying page read write. So we haven't added execute permissions at this point. We're just asking for a space in memory where we can write our shellcode. The reason why we don't add execute here right away is because Microsoft Defender or any other endpoint security product will get very suspicious if you're asking for read, write, execute memory all right off the bat. So that's why we're doing read, write there. And so the arrow is pointing to that code. So when we call the virtual alloc function, eventually it ends up going to NTDLL and calling the function NT-allocate virtual memory, and that actually performs the operation on memory. Next slide. So step 2, so once we've got the space in memory to move our code, we want to actually move our shellcode into that memory space. So on the left is my Microsoft Paint interpretation of that, where we have our malware.exe running in process A, and we want to move our shellcode as part of the .exe file into that process's memory space that we just requested. So then we get to the middle section of it. So the function call that actually does that, we can use write process memory to write our code into there. And then on the right-hand side, you can see now process A has shellcode in that memory space. The only thing I want to point out before we move the slide is in that middle section where we're doing write process memory, there's handle -1. We'll really get into this in process injection, but in this context, handle -1 just means we're doing it in the context of our own process. We're not writing to another process, we're just writing code in the context of our own process. Okay, next slide. So we've allocated space for our shellcode. We've copied the shellcode into that space. Now we need to adjust the permissions so that we can actually execute it. The usual function for this is called virtual protect. And so there you can see now there's that page execute read write parameter that we're passing. So that changes the permissions from read write to include execute. And that function eventually calls NTDLL again, calling the function NT protect virtual memory. And that'll actually change the permissions on the memory space. Go to the next slide for our last step. Is we need to actually execute that shellcode. So we've got the space for it. We moved the shellcode into it. We've changed and added execute permissions. Now we need to run it. It's pretty simple in that bottom screenshot there. You can see create thread, and then in the middle, we're passing it an ADDR variable, which is the starting address of where we got our memory space. And then we're doing a wait for single object, which isn't always necessary. All it does is says, hey, wait for that thread to finish executing. So if our shellcode takes a little bit to complete, we want to make sure we wait for it to finish before we actually close the program so our shellcode can actually do what we want it to do. But that's our standard workflow. If we go to the next slide, I think it's an overall picture of it. Yeah, so here's just as basic, bare bones, straightforward as you can get. So it's going through all the code lines that we've already seen. So we kind of in the middle there, we start seeing the virtual alloc to allocate the space. Then we're doing the write process memory to do the copy, virtual protect to change the permissions, and then those 2 lines to execute the code. The only thing I kind of want to point out before we move on is on line 3, so near the top, we have a variable being defined there called buff, which is a byte array. But here, instead of any actual malicious code, we just have one null byte, 1\x00. So nothing actually malicious being performed here, not yet anyway, but that's being defined in the code to be executed. So if we go to the next slide. So with that null byte, so this includes no malicious code whatsoever, or no malicious shellcode whatsoever, it is still alerted on by 9 EV EDR products when I uploaded it to VirusTotal at the time. So that's showing you that just that pattern, that allocate, copy, change permissions, and execute is identified as malicious by these 9AB EDR products. So even though it's not saying any malicious things, it's not doing any, like, without even sandboxing it at all, just that pattern of behavior looks malicious, so it gets flagged. We can go to the next slide. Because that introduces now our topic of defense evasion, obfuscated files, or information dynamic API resolution. Screenshot there in the middle is just from the MITRE page for this particular technique, showing that attackers definitely do use this dynamic API resolution in the real world. So let's get into it. Go to the next slide. So we'll talk a bit about the import address table. So when we take that program, make that full code snapshot that we had just seen, and we compile it, Windows wants to create an import address table within your program that says, here are all the kind of DLLs that you need and all the functions that your code uses out of those DLLs to keep track of what it needs to load and what your program is going to call. The import address table can be reviewed using Visual Studio's dumping command. We'll all see this in a demo in a sec, where we're calling bin/imports and then specify the name of our executable, and it'll show us all the functions that are defined within that import address table. If we go to the next slide, this shows the import address table for notepad.exe. So a typical standard non-malicious program. We can see at the top, kind of near the top, it says out of kernel32.dll, and then it lists a bunch of functions that it's going to use. Kind of in the middle there, you can kind of see create file, read file, things you would expect Notepad to do. I'm sure all the other functions are used somewhere else. But that's what it looks like for notepad.exe. If we go to the next slide, this is what it looks like for our little malware program that we had. So you can see it's out of kernel32.dll. It's just using create fed, virtual alloc, virtual protect, write process memory, and wait for single objects. So here. And so you can see why, without any sandboxing or without any malicious code, antivirus or EDR solutions might identify it as malicious because it's only using those functions, and those functions are commonly associated with the malware workflow. So if we go to the next slide. Sorry, one back. So how do we get around it? So the functions that we used in our first bit of code there, like virtual alloc and virtual protect, exist within kernel32.dll, which we saw in that previous screenshot of the import address table. So what that does is when we call virtual alloc, it goes to kernel32. Kernel32 does some parameter massaging, best way to put it, and then eventually redirects to NTDLL to perform the operation. So if you remember, when we had done that save file, it eventually goes to NT create file, right? So when we do allocate memory, so we call it virtual alloc, but the function in NTDLL that actually performs that allocation is called NT allocate virtual memory. So rather than call them like that in our code, like virtual alloc for virtual protect, it would be a bit sneakier if we were able to just find where those functions are sitting in our memory space and then call them directly, so we don't have to define them in our import address table. If we go to the next slide. So this slide is showing kind of those same standard functions that would be used, but the name of what we call directly. So on the left there, like virtual alloc is the function we would typically write in our code, but if we're able to find the NT allocate virtual memory function in our memory space, we can call it directly. And so the same with the rest of the functions that we use as part of our workflow. Write process memory is NT write virtual memory, virtual protect is NT protect virtual memory, and so on and so forth. I think if we go to the next slide, it's demo time. Yep. Okay. Let me share my window here for my virtual machines that I really hope didn't fall asleep. Cool. So here's the same code that we just looked at a slide ago. Allocate, copy, permissions, execute, that standard way. I did add some actual shell code in here. So this is just non-obfuscated or anything like that code that it will just launch the calculator application. So if I run this code, as my calculator pops up, and just to show the same thing as before, or from a couple slides ago, so I'm running the dump bin command. There we go. Okay. So if I run the dump bin command on this program that we just compiled, we can see the same thing from that slide we just saw a couple slides ago with those 5 functions defined in the import address table. So if I want to try to define those dynamically, this is how I would do it. Here's program number 2. It does the exact same thing as before with the exact same shellcode, just designed to launch calculator. And it looks kind of similar to the code that we just saw, but there are some differences. So I mentioned that we eventually end up calling, so when we do that virtual alloc call, let's say to get the memory space, we used virtual alloc before, but the actual function that performs that operation is called nt-allocate virtual memory. And so that function exists in ntdll, which we know, and we know that when we launch a process, ntdll is loaded into that process by default. So that function sitting somewhere in memory. We just need to find it so we can call it directly. And so Windows actually provides us functions to help with that. The first one here is called get proc address, so get procedure address, I believe is what it's short for. And that will perform that exact task. It will locate that function in memory. All it needs is 2 parameters. The first is a reference to ntdll. So Windows provides a second function to do this called get module handle. So we call get module handle and pass it ntdll. So that'll get us a reference to where ntdll is sitting in our process. And then the second parameter to get proc address is the function name we want to locate. And with those 2 parameters, it will find the nt-allocate virtual memory function in memory from ntdll and return the address of that function. And we assign it to a variable called p-virtual-alloc. And then you can see down below here on line 41, we call p-virtual-alloc. And the parameters look a little bit different than the last time we saw virtual alloc. There's some additional kind of types that are added, a couple of things we have to pass by reference. We didn't have to pass by reference before, but it is pretty similar to our original virtual alloc call. We just have to do some of the massaging ourselves. And then we repeat this process for virtual protect, is nt-protect virtual memory, write process memory is nt-write virtual memory, create thread, nt-create thread x, and wait for single object, we have pwfso. And then we call them in the same order, and they should work. And if I run it, the only other little bit of complexity here is the type that we have to give it. So I'll circle back to the virtual alloc functions. When we get a pointer to where that address sits in memory, our program still needs to kind of define what that function, the function structure looks like. So we need to tell our program what the return type is and what the parameters are that this function accepts. So when we find that address, we assign it to a variable, but that variable type has to be defined somewhere. So if I go to it. So those can be defined. So this is a different file in the same program, and I'm only going to walk through one here. But we add a little type def, so a type definition. We're saying this NT status is the type that is returned from NT-allocate virtual memory. And then we provided the details on the parameter. So it's very similar to virtual alloc, but the parameters and the types are a little bit different. So we define that in our program, and then that's what's defined here. And that's the type of our variable that gets the address, and that helps us call it properly. But in all those elements, we're able to run essentially the same workflow, but calling those functions directly in memory rather than using the ones from kernel32.dll. And if I use the same tool here, so the same dumping tool, and so this is the import address table for the program that we were just looking at with the dynamic function calls. And you can see now those functions are no longer within our import address table. The only things in there are get proc address and get module handle, which helped us find those functions dynamically in memory. So now our 5 functions that were key in our malware workflow are now no longer visible in the table. And so you might be thinking, well, why don't we just alert them when we only see these functions? That's true, you could, but there's also nothing proprietary about these functions. You can certainly rewrite your own implementation of these so you can avoid these being in the import address table as well. But that is demo number 1. So I'll stop sharing and I'll go back to the presentation. Here. Okay, great. So where is this in the real world? Happens in a lot of places. That MITRE screenshot to start was probably the better option, but I did want to find some real code to show. So I found this piece of malware on GitHub called Predator the Stealer that rips data from browsers, programs, reports on system information and such. And you can see a kind of a similar workflow going on in the screenshot below, where they're using get proc address 64, which is their own custom implementation of get proc address. and then they give it get ntdl64, which is their own custom implementation of get module handle to find ntdl in memory. And then I'm not going to get into the source string obfuscation piece of it, but you can see similar function names being passed there. And so this program is also locating those functions in memory, and those functions don't have to be declared in the import address table. But I think that's it for IAT obfuscation. If we go to the next slide. So that IAT obfuscation is by no means a silver bullet. Like it's not, it's not going to defeat all AV EDRs, but it is a good way to kind of make your program a bit sneakier right off the bat. So now we're going to get into pairing defenses to similar modified tools. So here we go to the next slide. Great. So now we've kind of talked a little bit about API calls and writing to memory, virtual protect, changing permissions in memory, and that kind of thing. So AV EDR solutions, so desktop endpoint security products, whatever, will now, so regardless of whether or not you call them using virtual alloc or the standard way, or if you're calling them using them directly in memory, in AV EDR, we'll still want to look at what you're doing. So they will add hooks to specific API calls so that when we call, whether we call virtual alloc or NT-allocate virtual memory or however we do it, whenever we get to that actual function that performs the operation, that AV/EDR will redirect code execution to their own code space where they can do analysis and determine if it's safe to perform the operation. So if we go to the next slide, and I think I might, yeah, and just go to the next slide. It's a little bit clearer. Okay, yeah, we'll stop here for a sec. So, so we're talking about the AV EDR's hooking specific functions. In the screenshot is the actual assembly of what that function, of what all these kind of functions look like. So whether or not we're performing NT-allocate virtual memory, NT-protect virtual memory, or any of the other functions that we've talked about, when they eventually go to NTDL and execute code, this is the exact code they're executing. They all look near identical. And we definitely aren't going to get into the depths of registers and all that stuff today, but I will walk through a little bit of what it's doing. So the first line, move R10 to R6, again, register stuff, but what that's doing is preparing parameters. So regardless of what the parameters are to the function, this particular code is getting it ready to actually be performed at the kernel level. The next line, move EAX18, is setting the operation code. So this is setting what function is going to be performed. So like NT-allocate virtual memory in this case is 18. That's in hex, by the way. But the next function down, let's say, I don't know what it actually is, but let's say it's deleting a file, then that code would be 19. Maybe virtual protect is the next one. That would be 20. You kind of get it. The operation code shifts as you go. The third line, so then the next two lines, when let's say test byte and JNE, are doing an architecture check, so checking if your system is 32-bit or 64-bit. We don't really care about that today. And then after that, it calls the syscall instruction. So this is the syscall instruction changes the execution mode from user mode to kernel mode, where it actually performs the operation on your hardware. You notice there's no parameters or anything like that to it. It's responsible just for changing that execution context and running whatever the operation is that you specified in your operation code. But that function structure is identical across all the functions that we've talked about today. It's the identical code. The only thing that changes is line 2, where the operation code changes. So this is all without an AV and EDR installed. Let's go to the next slide. So we installed self-host EDR in the system, and now our function call looks like this. So the bottom kind of looks similar, but we have the same syscall instruction. There's that int2e that was there before. But then above that, it kind of gets really messy, right? There's even question marks in there telling me it's probably not even a valid assembly, and some weird adds that we didn't see before. And I don't see any of my kind of parameter preparation or operation code setting. But at the very top, there's a jump instruction. And that jump instruction is going to a memory address. So naturally, I want to see where's that jump address taking us. So if we go to the next slide. So using x64 DBG or any kind of Windows debugger, you can follow that jump address, and it will show that that jump is going to the code space of another DLL called hntalert.dll. So if we investigate this, so just going in using File Explorer, going to System32, finding that hntalert.dll, right-click, go to Properties, and then under the Details tab, we have all the information there. Something called Hitman Pro, but at the bottom where the copyright is interesting because it says Sophos, right? So that's telling me that whenever we're doing this particular call, the code execution is going to a Sophos DLL, and Sophos is doing its investigation before that syscall is actually issued. That's interesting, and as an attacker, I definitely want to circumvent this or get around it. So go to the next slide. Right, okay. So when we launch a process, so like notepad.exe or what have you, all those DLLs were loaded in by default that we saw in that first screenshot, right? NTDLL was loaded by default, kernel 32 is loaded by default, there was a bunch of them. So when we installed Sophos, Sophos takes that HMP alert DLL and adds it to the list of DLLs that are loaded by default. So when it does that, it then modifies NTDLL in memory to add that hook that we just saw, to modify those assembly instructions to redirect execution to Sophos. But the original NTDLL file, so the one that's not modified, doesn't have any hooks in it, is unchanged, and it's still sitting in System 32. Sophos just does the changes to NTDLL in memory, which is important for a second here. If we go to the next slide. So what is the natural attacker response? So because there's an unmodified version of NTDLL sitting in System 32, an attacker or us can load that unmodified version into our memory space again, and then overwrite the hooks or all the instructions that Sophos changed. We can overwrite them again to put the original ones back in place and remove all those hooks. So you can get it out of the System 32 directory. If you're attacking a specific type of Windows operating system, you can pre-download it or have it hosted in the web, however you want. But the general idea is the same: to put an unmodified version of NTDLL into memory, overwrite the one that was modified by Sophos or your AV EDR, and then continue execution. So if we go to the next slide, I think it's demo time. Yep. So I'll share my screen again. Show this for a second. So here's the code that we're going to try to run. If I have time at the end, I'll circle back and go in depth on these functions, but I don't think I'm going to have time, so we're going to skip over them. But this function is responsible for getting the NTDLL file out of the System 32 directory, so the one sitting in the file system that's not modified, and it puts it into our memory space. And this function is the one that goes through and takes all the code that's unmodified, the original one, and overwriting the one that Sophos did. So if that function fails, the program will exit. But if both of those functions succeed, then we'll see a message box pop up just saying testing. So I've compiled this program and moved it to a virtual machine with Sophos on it. So there's the little Sophos thing, just showing you Sophos is installed. Here's the compiled program called demo NTDLL. And the tool I'm using here is the Windows debugger. So it's very similar to the X64DBG tool. X64DBG was crashing on me a ton when I'm seeing this demo. So we're using the Windows debugger. This is like X64, but officially from Windows. It can be a bit messier in my personal experience, so I don't like it as much, but that's what we're seeing today. So all I did there was I just had Windows debugger open and run my program, so nothing odd has happened. And then it's paused it right after all of its initial setups and loads. So I've run this demo ntdll.exe program. We can see it's loaded the ntdll file. The hmdlr.dll file is loaded into memory, and then there's the rest of the DLLs that are getting loaded by default. If I run that line there, it will show us the actual memory and assembly instructions that are sitting in the memory of our current process. So I specified the ntdll file and ntallocate virtual memory. And we can see here that it's got that jump instruction. There it is, along with those weird adds and the question marks and such. So it didn't show me, but this address, so this jump address is going to that hmpalert.dll file. But our program is paused, right? So it hasn't launched quite yet. So all Windows DBG has done, Windows Debugger has done, is launch the exe, but paused it right after it's done all of its DLL load. So it actually hasn't started running yet. But I just wanted to show that that function is hooked in memory. If I hit G, so that just means go resume. The only other interesting thing to see here is that NTDLL is loaded again for a second time. So that's our program loading that file off disk and overwriting in memory. And we can see our message box is up. I pause this, and now I look at the memory space again. So I'm looking at that NT allocate virtual memory again. We can see that the assembly is restored. So this is now the original version without the hook in place. So by doing that, we can get around any user mode hooks that an antivirus or EDR might place when our program is running. But I will mention, like, these are all, I keep using the word user mode, so these are all things that we can change. EDRs certainly have ways of doing things at the kernel level, which are not as easily bypassed. But just when they add these user mode hooks, they can be kind of bypassed pretty easily when you overwrite their NTDLL. So I'm going to stop sharing. We'll go back to the presentation. So detection, so that code we just run does still get detected even though it's not doing anything particularly malicious. Still 7 out of 72 vendors are saying, hey, something's funky with this program. So still pretty good detection on that. But we did drop 2 of them in the process. So real world example, so Conti ransomware used this. So Conti ransomware, big in the news a couple of years ago. I don't think as much today, but they're probably still active. And those screenshots at the top are from their actual code. So in the top left, you can see they're doing a remove hooks on NTDLL, and this all eventually ends up in the disable hook function in the top right, showing that they're doing some load libraries on specific DLL files. So load library is just another way to load that DLL into memory space where they can eventually do the overwrite. But yeah, definitely used in the real world. Detection. So when I was running different malware loaders for different assessments, I was going up against the Elastic security product. I noticed I got detected, but not only did it get detected, it specifically called out that NTDLL was getting unhooked, which I thought was interesting because if they're able to do it, like why isn't everybody doing it? So if you go to the next slide, just almost like a little self-plug. I wrote this little program called NT. You can go to the GitHub there to view its code. Just a little proof of concept piece that will do the scanning, so it'll check for duplicate NTDLLs in memory, or if your antivirus EDR tampers or adds hooks, it will check for the original untampered one in the memory space. So here's me running it. And then at the bottom there, it says, hey, I found multiple instances of NTDLL in this particular process, which happens to be my code loader. So just a little plug there. Feel free to check out the GitHub to review the code if you're interested. But that's NTDLL loading. Now into process injection. Yeah, we can just go to the next slide. So very similar workflow to what we initially looked at with the allocate, copy, change permissions, and execute, almost identical. The only thing that we're going to change here is we're going to find a process to inject into. So that's step 1. I have to go to the next slide. So here's kind of a workflow for it. So on our left is an example again where we're running our malware.exe as process A, and we want to move shellcode into the space of process B. So then our middle section gets into it. So I'll get into the code here. So the first line there is running a function called getProc by name. That's not a Windows function, that's a custom one. But all it's doing is looking at the running processes on the system and checks if any are running with whatever name we provide it. So in this case, notepad.exe. And if it does find one, it will return the process ID in a variable called PID for us. If that PID is 0, we just exit the program because we didn't find a process. But then if notepad.exe was found, the line at the bottom there, popenproc, is a dynamic call to the open process function. And then in the second parameter, we're saying process all access. So what that's doing is it's going to the notepad.exe process, and we're asking for full permissions on it. So often if they're running under the same user accounts, you can do that, but occasionally it's not. And so you can, instead of process all access, you in theory could ask for different permissions. Maybe if you're just trying to read the process information or whatever, restricted permissions. But anyway, in this case, we're opening up a full permission handle to the notepad.exe process. And if it's successful, it will return that handle or reference to the remote process in the P1 variable. And then the screenshot at the bottom is showing very similar code to what we've already seen, virtual alloc, write process memory, that kind of thing. But then you'll notice we're not saying handle -1 anymore, we're saying P1. And that's quite literally the only difference. So instead of saying handle -1, we're just specifying nope, instead do it against this remote process. Occasionally, you'll have to change the function you use, like create thread becomes create remote thread. They boil down to the same function NTDLL anyway, but there are some minor changes like that, but for the most part, you're just changing the handle that you're passing. And then on the right-hand side, after that write process memory occurs, the shellcode is written to the space of process B. Go to the next slide. So this is going to be a demo. I'm going to skip it just because it takes a little bit of time, and I don't feel like we're going to be running short on time by the end of the next demo. So I'll skip it, but what I will mention is that the last slide of this presentation is an appendix slide with a link to the GitHub, and that GitHub has all the source code for all the demos. So if you're really interested in seeing it, it's up there, that GitHub that you can find at the last slide. Oh yeah, but talking about process injection in the real world before we move on, happens all the time. So the screenshot there is just from the MITRE page on process injection showing APTs and threat groups certainly use it. The topic that we just discussed is about the most straightforward process injection way that you can do, that we could do. There's another much cooler, sophisticated way called reflective DLL injection or reflective injection, where you specifically map a file into a remote process memory to do it rather than just getting a handle on it. It's really cool, but out of the scope for the presentation today. Anyway, we can go to the next slide. Oh, again, I just wanted to find some real-world malware code that did something like this. So I found this remote access tool called TrollRat that uses process injection. So just the code here showing an example of us getting a handle to that process, or not us, but the author getting a handle to a remote process, opening it, and then performing operations on it. And we're good to go to the next slide. Detection on that same, on kind of that similar code, but targeting another process, we're getting 772 detections, so 2 dropped, but still pretty good detection on that front. Go to the next slide. What do we have for defenses against process injection? So testing your AV/EDR. In theory, in a perfect world, if bad code runs in, if you have bad shell code running in malware.exe, you detect it, and if you have bad shell code running in notepad.exe, you detect it. So you'd like to think that that detection is the same, but it's always good to test. And then secondly is monitoring for anomalous process activity. So, you know, if Notepad is communicating every 5 minutes to some weird internet address, then that's probably process injection and not valid Notepad code is running. So that's another way to detect it. Cool, so this is the last topic that we have for today about DLL sideloading. This is super cool, and we are gonna walk through the demo for this. So I'll talk about high-level workflow of the total attack, but it'll probably be a lot clearer when we do the demo. But for a general idea, if you take a file, like let's think of Notepad again, and if we take Notepad, the original Notepad sits in C, Windows, that System32 directory. If we copy notepad.exe to our desktop and run it, instead, notepad.exe will look in its current directory, wherever current directory it's sitting in. So if it's in our desktop, it'll look at all the files in our desktop for all the DLLs it needs to try to launch. If it fails, so like it's not going to find ntdll.dll sitting on our desktop, it'll fail, and then it will eventually go and find the right one in System32. But that first little look, where it looks in its current directory for the DLLs it needs, is an opportunity for us to put our own DLL in and strategically name it, so that when we launch notepad.exe, it loads our bad DLL, and then we can eventually get code execution under the context of notepad.exe or whatever valid process we're targeting. So from a high level, that's what it looks like. You can go to the next slide. Step one is moving a executable into a user writable directory. So for this attack in our demo, we're going to be using explorer.exe. So that's associated with Windows File Explorer. If you don't know what that is, it's just a little folder icon. So when you click it, you can browse your documents, your desktop, what have you. That's the File Explorer, and it runs under a process where it uses the explorer.exe executable. So all the screenshot here is showing is that I'm copying it out of the Windows directory, excuse me, and into a directory called demo on my desktop. So it's just sitting there all by itself. Go to the next slide. The first screenshot at the top there is showing what happens when we run explorer.exe from the desktop. The screenshot is out of Process Monitor, which we should see in the demo. But when we run explorer.exe in that demo folder, it starts looking for any DLLs it needs in its current directory. And that kind of proves it, right? So you can see here it's looking for aepic.dll, and the result is name not found because that DLL doesn't exist. And it goes through the list of DLLs it needs to launch, and they're not found in our current desktop, then it eventually goes and finds them in their correct directories. But the one that we can target, or the one that we will target, oops, sorry, go back, is kind of in the middle there, called dxgi.dll. So if I want to have my code loaded by explorer.exe, I could take that same code that we've been running today with the allocate, copy, change permissions, and execute. I can compile it as a DLL. If I can then change the name of that DLL to dxgi.dll, put it in the directory on my desktop that I can actually write to, and next time I launch explorer.exe, instead of name not found, it'll find that DLL there and load that DLL into its process. So then our bad code would be sitting already in that explorer.exe process. But it is a bit of a trial and error because if, let's say, explorer.exe is using dxgi.dll for some critical function, and then we masquerade ourselves and disguise ourselves as dxgi.dll and get loaded into the process, then explorer.exe might crash because it can't actually call the functions it needs to keep running because we've kind of taken over them, right? So it's a bit of a trial and error of going through DLLs and all of its functions to find which is one that we can successfully mimic ourselves as without crashing the original process. So the screenshot at the bottom is showing us doing that, and this, again, it'll be clear in the demo. So the bottom screenshot is showing when we launch explorer.exe from its regular directory without changing anything, so C Windows explorer.exe, we launch it with a debugger, and we pause it, and we look at all the functions in, if we're targeting dxgi.dll, we look at all the functions that are being exported from dxgi.dll, which is what's shown in the screenshot there, dxgi report adapter configuration, dxgi declare adapter removal support, and so on and so forth. We set a breakpoint on every single one of those functions and then resume the execution, and we wait. And so if we see that second line is a little bit more black than the others, that's because that breakpoint has hit. We've hit a breakpoint, but explorer.exe tried to call dxgi declare adapter removal support, which is good news for us, right? So now we know if we take our malicious code and we export a function from our malicious code called dxgi declare adapter removal support, we compile it, we rename our malicious DLL to be dxgi.dll, put it beside explorer.exe in the user writable directory, and we launch explorer.exe, it's going to load our malicious DLL, it's going to look to call dxgi declare adapter removal support. So because we've defined that our malware code, explorer.exe will call that function out of our DLL, and then our custom bad code will run instead of the expected code, and then explorer.exe is running our bad code as part of its process. So all sounds very nice and very confusing. If we go to the next slide, I think it is demo time, or maybe not quite yet. No, we got one more slide before demo time. So kind of just walking through a little bit of what I've already explained. So once a function is found, so we found that dxgi declare adapter removal support was called by explorer.exe. So in our code now, we add this little block to the bottom that says, hey, we're going to have a function also called dxgi declare adapter removal support, but we're going to have it just called the run function, which in this case is just the main function that does all of our main malware stuff. All the stuff before the name dxgi declare adapter removal support, that extern decospec DLL export, is just syntax to get it exported from our program. And that's what the screenshot at the bottom is showing. So if we run that dumping tool again, but instead of /imports, we say /exports to see what functions are exported, we can see one function is declared at the very bottom, and it's that dxgi declare adapter removal support. So if we go to the next slide, I think now it's demo time. No, not quite yet. One more to go. Okay, yeah, so here's us copying. We've compiled our malicious, we've put that dxgi declare adapter removal support function in our malware code, compiled it as a DLL. Now we've renamed that DLL to be dxgi.dll, and we've put it beside the explorer.exe file in the demo folder on my desktop that I have write access to. Now we run explorer.exe, and if we go to the next slide, I think still not demo time. At the top, the first screenshot there is the same kind of events that we saw when we initially ran it, and it was all of those DLLs that were trying to be loaded and the name not found on the right. And here, at the bottom of that screenshot, you can see it's doing that same look for dxgi.dll, but this time it's reporting success because we've put our malware beside it. The screenshot at the bottom is showing the breakpoint being hit at the start of our malicious code. You can see on the right-hand side of that screenshot, NT allocate virtual memory and deprotect virtual memory. All those functions that we're using as part of our malicious code, those are all about to run because the explorer.exe has now officially transferred execution over to our DLL. Now if we go to the next slide. Now it's demo time. Okay. Oh no, my VM paused. What happens? So we'll sit here for just a couple of seconds while my machine boots up. Sorry about that. Cool. So I'll actually take a second to show the code. So here's the code that we are compiling as the DLL. So the same shell code is there to pop a calculator. Here's the run function, which looks identical to the that IAT code that we looked at to do the dynamic resolution and execute. And then all that we added at the bottom was that function that we already saw, where we're saying, hey, we have a function called DXGI declare adaptive removal support, and it calls the run function, which is that function with all of our bad code. So if I come to this, so you can see it compiled to a file called demo_SL. So here I've just got a directory in the C tools directory called demo4. It's completely empty, but I can write to it. Oops, that's just there. And then after copying that, I'm going to copy C Windows explorer.exe. Yeah, okay, great. So I've got the two files here. So I'm going to rename the malicious dxgi.dll. And so there we go. We've got the two files sitting side by side. And I've got process monitor ready here. So process monitor is configured to show me, it's going to show me the ones from the regular explorer.exe. Process monitor right now is configured to show me all events from any process named explorer.exe or calc.exe, just for that calculator boot. Here's x64.dbg, and I'm going to use it to open up. So I'll go to that demo folder we just created, and I'm going to say, okay, let's launch explorer.exe. Wait for a sec, nothing crashes on me. Great, so here we can see explorer.exe has launched, and then it lists all the DLLs that it has loaded as part of its process, and then it's paused again right before the program actually launches. It's done all its loads. So if we go to the dxgi.dll entry, you can see in the path here, it's the one in C tools demo4 dxgi.dll, not the one in system32. And if we look at the exported functions on the right, we can see the function that we defined right there. And there's all of our dynamic finds, right, for NT allocate virtual memory, protect virtual memory, blah, blah, blah. And we've got a breakpoint set at the top. So we're going to make sure process is running. It's picking up a bunch of events from the explorer.exe. That's not ours. Maybe I should probably close explorer.exe to avoid that. There we go. Okay. And so now if I resume execution here, I'm going to have to do it a couple of times, but there we can see our breakpoint is hit. It has found that dxgi.dll. I'll see if I can quickly see it. If I don't quickly see it, we're just going to go by it. See the properly, must have something misspelled. By the way, our function hits. So that dxgi declare adaptive removal support function is called by explorer.exe. And if I continue execution, we should see explorer.exe launches along with our shellcode running and calculator is popped. Let's go down to the bottom here. Let's take file out of it. You can see here, there's the calc.exe getting launched by explorer.exe. So that's a good way to kind of disguise your execution. So when you're running code, I don't run, the process doesn't look like malware.exe running. It looks like the valid explorer.exe is running. It's just loaded in a code dependency that we've kind of mimicked or we are masquerading as. And in that way, if AV, EDR, or an analyst isn't looking to say, hey, did explorer.exe or whatever process launch out of the expected directory, then it might go, it might not get caught right away because it looks like it's a valid Windows executable. All right, I'll pass it back to Cliff. So I think I got a couple more slides to talk through. Yeah, so using that method, so with the exact same code that we just did, not with the malicious calculator shellcode, but just the technique of doing that DLL side loading, it's only 272 detections. So we went and dropped 5 of them. So now we're not going to get detected nearly as often, right? I will say a lot of that I think is probably just because we changed our program is no longer a .exe file, it's a .dll file, which often gets a lot less scrutiny by AV EDR. So that could be a couple reasons for them dropping off of our detection list there. I think I might have one more slide after this. Oh, right, just showing that, there's plenty of examples of DLL side loading happening in the real world. This is a screenshot from the MITRE page. You can certainly see more details if you head to their attack framework page, various APTs and threats that's using this technique. Go to the next slide. There, now I'm done and I'll pass it back to Cliff.
Cool, thank you, Wade. It's a real brain melter for sure. So lots covered in less than an hour. That's many years of research boiled down very well. So how do we use malware in a security assessment? So a bunch of different ways. One of the ways is we want to test things, like sometimes we have to get by something like Sophos. So as part of our red teaming test, we're doing things to try to get by what you have built on there, especially looking for misconfigurations, those types of things. So of EDR. EDR is a great tool, but it isn't a set it and forget it. So it's good to test it in order to validate what you think you're doing. You really are doing. The other thing is to make sure. Well, one of those things that Wade was showing was that DLL side loading. For sure, there are protections against many applications to prevent you from looking in that same folder. But we've definitely found lots of applications, especially some services that run that don't do that type of thing. So that's another way where we're using something like malware. It's not really malware, but it's malware because it's not intended for you to run it, but it's for us to run it. And it's been successful. And of course, we don't actually just go to VirusTotal and download whatever the latest malware is. We are writing custom things, like Wade said, it's very bespoke things. And it's just a good thing to do to make sure your protections are in place, because if you aren't assessing, you're just guessing. So if you have any questions, of course, you're welcome to put them into the chat. If you would like to know more about us, please click on the QR code. It's safe, I'm sure, and go to arctic.com services, penetration testing services. In case you didn't notice, we have pictures of cats. So the team is called the Cybersecurity Assessment Team. That's what I called us, CAT. So we're the cats. Yeah, and as mentioned, Wade has all this different demo code up on the GitHub. So. Good. So any questions or anything, please put them in. Otherwise, I thank you very much for your time, and it's right on time. I'm not seeing anything, so thank you again. Until next time, it's been a pleasure, and thank you very much, Wade, for all the lessons learned.